ओके चालू कर दी दो चलो इलेक्ट्रिक फील्ड and electric charge, chapter number 1. So yesterday we see the some characteristics of field line. Okay, some characteristics of field line. Characteristics of field line. So what are the characteristics of field line? Say one by one we try to analyze. First of all, first part is that electric field is outward outward for positive charge. Electric field is outward for positive charge. How can we understand that? So that is the positive charge and it is outward like this way. Then second, electric field is inward for negative charge. Means how can we draw? This is a negative charge, direction is like this way, inward direction, this is the inward direction, this is outward direction, so this is the way. Clear. Now third, as we see the equation of electric field E is equal to KQ divided by R square. Meaning of KQ divided by R square is what? Meaning of KQ divided by R square means what? That E proportional to 1 upon R square, means electric field as R tends to infinity, E tends to 0. As R tends to infinity, E goes to 0. It directly means that for a local or say for some amount of distance in centimeter or meter, there is existence of electric field. And as we draw some simple graph over here, so how one can understand the simple graph? See, there is a simple graph over here. Here. So that is the R, E versus R, and your graph should be like this way. So that is 1 upon R square characteristics graph. Clear. Furthermore, there's a characteristics of electric field lines as told by Michael Faraday. Michael Faraday says that electric field is real, but field lines is imaginary. It is not real. Electric field is real, but electric field line is an imaginary. So what about this? Electric field is real. Can we write down over here? Electric field is real, but electric field lines are imaginary. Electric field lines are imaginary. Further we can understand, once again we draw the field line decreases, field intensity decreases by increasing the distance. How? You see, field lines decreases or intensity of field lines decreases as the increase the distance. How one can understand this statement? By this equation. As you know that R is increasing, E tends to 0 by this graph. One can understand properly. So see, initial field line strength is higher, then continuously line is decreases. intensity of field lines decreases. This is for positive charge particle. And similarly, for negative charge particle, how one can understand? See, initial field, negative charge field lines is inward direction. Negative field lines are inward direction. These are the negative field lines which are inward direction. And as you increase the distance, the field line strength decreases. The field line strength is decreases. As you see, this is the field lines. By this equation and this graph, one can understand the strength is decreases continuously for positive and negative charge. The strength is increases and decreases for both of the ways further. Further in the case, one can understand, see, number 5. Two field lines never intersect at each other. Two field lines never intersect at each other if they intersect. Then we obtain two direction of field line. Direction of field line, which is not possible. The meaning of this is what? Suppose this is the first field line as it passes through this way. Say this is the second field lines, they intersect. If they intersect over this point, so how one can identify the electric field line? At particular point, draw tangent to that point. If you draw tangent, so first electric field lines in this way. If you draw tangent over here, the second field lines here, the second field line is here. Clear? Tangent to this way. So you see, at only one point, you obtain the two different position of particular electric field line, which is not possible. Electric field have only one direction. So this statement is wrong. Means two field lines are never intersect at each other. They never intersect. Similarly, means suppose you are at home and exactly at that instant you do not present yourself in your school or in your tuitions. That is the main key point. To understand this point, that electric field lines are never intersect each other. They have only one direction, not the different direction. Okay. By this way, one can understand properly that electric field lines are never ever intersect. Number 6 point. Electric field lines are equidistant. Electric field lines are equidistant and parallel. Electric field lines are equidistant and parallel. What does it mean? Equidistance and parallel, what does it mean? If you can properly understand what do you mean by equidistance, you can draw the field lines properly. Electric field lines are equidistant like this way. One can see this electric field line equidistance. You see, everywhere there is the same distance. So, same distance, and that's why they are parallel. So, named as equidistance and parallel. But one can understand these point on another way also. So, if it is not equidistance, means how you represent that field lines? You can see properly. So they are not equidistant by this meaning, although they are parallel, but they are not equidistant. You see, this distance is different, this distance is different, this distance is different. Okay, so that's why suppose this is the D1, this is D2, this is D3. So in this case, D1 does not equal to D2, does not equal to D3. So they not equidistant. So they are not equidistant and this equidistant. Although they are parallel, but not equidistant. So that's why this point is arise over here. So these are the field line characteristics. Furthermore, if you want to find out the field strength, if you want to find out about field strength and how one can find out the field strength, number 7. For field strength, for that, suppose I take the unit positive charge to find out the field strength. Suppose I take the unit positive charge and draw the field lines over here, outward normal, unit positive charge, and I draw the outward electric field lines like this way, outward electric field lines. Okay, good. These are the outward field lines. And if you draw a unit square, suppose you draw the unit square over here, and same unit square you move to here, same amount unit square to here. So there is the probability of find out the field strength by this concept. How? If you have a unit square and put it near to the positive charge, you see the field lines which is passes perpendicular to the unit square. Not necessarily all the case that is passing perpendicularly. Means suppose there is a unit square and that is the perpendicular. That is the perpendicular, one can understand. That is perpendicular. Good. That is perpendicular. But not necessary. It is anyway direction it is passing from here. But main key point is that it is passing from that. So due to this, if the number of field lines is increases, if the number of field lines increases passing from this, then the field strength is larger at that point. If the number of field lines are smaller passing from that, one can understand that there is a smaller or low intensity electric fields. So one can understand near to the charge, near to the charge, field lines passing from it are larger. Field lines passing from it are larger. So intensity is larger. Intensity is larger. Field line intensity is larger at this point. If the field lines is passing from this unit square, then it say there is a higher intensity electric field strength. Electric field strength. Electric field strength. And if you move this square away from the positive charge, you see properly that less number of field lines is passing from it. Less number of field lines passing from it. So low electric field intensity. Electric field intensity. Low electric field intensity at some distance, at large distance. So point to be worth note over here, why it is so. And with the help of this topic, what we can understand? Two main topic you can understand from here. First one is that you can identify the field strength, where is larger and where is smaller, or a higher field strength and lower field strength. And second point, one can note that the field which is imaginary, you can calculate it. A number of field lines, you can calculate it. Faraday gives the way to calculate this the field number of field lines. By this way, the second point is worth to note, that is named as flux. The another way it is named as flux. Flux means that the density of field lines which is passing from the unit square density, and with the help of this density of field lines you can identify the intensity, at which point the intensity is larger and at which point its intensity is lower. That is it. So these are the worth point is noted over here. So it is the characteristics of field lines. Move further. Further we move and continue with this point, gives you the new theory named as electric flux. Okay, before we start the new topic, just rearrange all the terms once again or summarize the topic, what we learned in this topic. First, field lines characteristics. First, from positive charge, field lines is outward. From negative charge, field lines is inward. Second thing is field line is inward and negative inward direction for that. Third point, if you know that E proportional to 1 upon R square, the graph of E versus R is like this way. Graph of E versus R is like this way. The fourth point is that electric field lines is real, but field lines is imaginary. Field is real, but field lines is imaginary. Field is real, but field lines are imaginary. You see. Fifth point, note to understand by this equation, as the value of R is increases, directly proportional electric field line decreases. You see this. As R is infinite, R tends to 0. So first field lines from the positive charge, which is outward, you see the field line strength, length of this field line near to this positive charge is larger. As you grow, further move outward, field lines, length of this field line decreases. You see, length of field lines decreases. Similarly, from here also, from negative charge inward direction, but field lines length, you see, this length is larger, this length is smaller, this length is further normal, smaller. So one by one, we can understand the field intensity gets lower. Fifth point to be noted, two field lines are never intersected each other. If they intersect, then we obtain the two direction of the field lines, which is not possible. You see this graph point, first field line, second field line. You see at first field line is in this direction, the second line is this in this direction. So which electric field exists over there, which one cannot understand. So two field lines are never intersect each other. In this case, we apply same in a magnetic field, same in a gravitational field, and same in a streamline flow. Same in a streamline flow. So this is the point to be understand. Sixth point is that electric field lines are equidistant and parallel. See, equidistance means everywhere there is the same distance. With the help of the same distance, they are parallel. And if they are not equidistant, then after they are parallel. See, distance is not same, but rather than that, they are parallel. So that is another point to be understand. So there are two types of electric field lines, uniform and non-uniform. Uniform field lines is that they are, uniform field lines is that one can understand, you see, that they are equidistant and parallel. Uniform field lines is that. And non-uniform electric field is like this way. These are the non-uniform electric field lines. So they are at distance is increases. They are not equidistant, not parallel. That type of field lines is named as non-uniform electric field. And seventh point to be interesting to understand this way, that field lines intensity larger near the point, near the charge, and large distance, the field line strength is decreases. Field line strength is decreases. That is the key point to understand. Means if you have a unit positive charge, if you have a unit square, unit positive charge, and take a unit square, put it near to the charge, the number of field lines is passing from it is higher number. So at that point, intensity of field lines is higher, and far away from that, intensity of field lines is smaller because low number of field lines passing from that unit square. With the help of this, one can calculate the flux, electric flux from this. So move the second theory with the help of this point. The new point is this, that electric flux. So how one can understand electric flux? You can see the new point is electric flux. Electric flux. So how one can understand this electric flux? For that, once again, draw the field lines. Once again, draw the field lines. They are parallel and equidistant field lines. You can understand properly. Suppose you draw parallel and equidistance field line. So this is the parallel and equidistance field lines. Okay. Now, suppose I put a unit square over here like this way. I put a unit square like this way. You see in the shadow portion, there is a clearly field lines is there. They are parallel. And if you just move this square, you see field lines are tilt. Field lines are tilt means this square tilt, which makes some angle with this field line, with this field lines. So flux, how you calculate the flux or electric field line density, you calculate by this simple way around with the help of GC, the shadow portion over here. Okay, so calculate it. How you calculate C? Suppose you put a unit square, and that unit square you put it any direction. Suppose you put it like this way, unit square. Suppose you put a unit square like this way. Great. That is the electric field, and there is another new physical quantity named as area vector. Area vector is a physical quantity in such a way that direction of this area vector is always perpendicular. Direction of area vector is always perpendicular, and the value or magnitude of this area vector is the magnitude of this square, magnitude of this surface. The length of that area vector is, or magnitude of this area vector is the magnitude of this square or area, and is always perpendicular to that surface. So similarly over here, area vector have particular this direction. So you draw the area vector in this direction, you see, which makes some angle over here, theta, or say what to note from here, if we draw the direction, you see, which make an angle theta over here, this or this whatsoever. So in this case, one can understand properly that you make this area vector, this is the area vector, A direction, which is perpendicular to the surface. Make the component of area vector along the direction of E, or make the component of electric field along the direction of A. You make both the case, and both are right. Understand? Meaning is that component of electric field along the direction of A, or direction of A, component of A along the direction of E. We need to understand the component. Component means maybe you obtain the component of electric field, and maybe you obtain the component of area vector. Both the case you are right. So how one can understand this? Component means what? You obtain the projection. See how you understand the projection. This is the one vector, say vector A, and another vector, say B. You want to find out the component of B along the direction of A. You want to find out the component of B along the direction of A. Angle between them is theta. So what to do? So draw a perpendicular from the head of whose vector we want to find out the component. We want to identify the component of B. So draw perpendicular from head of B to the vector A, that is named as projection. Projection means what? It is not the meaning perpendicular is the projection. Perpendicular is not the projection meaning. The distance of this vector or the length of that vector is named as projection. Length of that vector is named as projection. Yes. Means by simple way you can understand. Suppose you have a torch and you just give a torchlight to this B vector and you obtain the shadow portion over here of vector B. That length of that shadow is named as projection. Length of this vector B is named as projection of vector B, named as projection. This is named as projection. This perpendicular does not mean that is a projection. Perpendicular, it does not mean it is a projection. Projection is this, the length of particular vector on another vector. That length is important. Get it? So vector B, length along direction of A, that is the projection. And how much? You see, that is the theta. There's a 90 degree. Opposite to 90 degree, it is hypotenuse. This is theta's adjacent side. This is opposite side. And if it is the adjacent side, that is the B cos theta. By the definition of cos theta is equal to adjacent divided by hypotenuse. So that is the B cos theta multiply A. And you see B cos theta into A. B cos theta into A. So you understand multiplication of these two gives you the new physical quantity. Similarly, same also over here. That is the A cos theta component. A cos theta component, projection of A along the direction of E vector, means you draw perpendicular on electric field, means you draw perpendicular on electric field. That is the key point. Draw perpendicular to the electric field in this way, perpendicular. Understand? So this projection of is A cos theta, and A cos theta multiply E. A cos theta multiply magnitude of E gives you the new physical quantity named as flux. It is named as flux. E is flux, or say electric flux, or say electric flux. Only flux, because flux is of two types: electric flux, magnetic flux, gravitational flux. That is another point. Clear? So that is the new equation arise over here, that flux phi, and there is a cos theta, and everybody know that cos theta as a dot product. So it is vector E dot vector A. If there is a cos theta, then there must be two physical quantity. It is a vector. Two physical quantities a vector. If there is a vector, then we need a cos theta, and cos theta means there is a theta point. Means there is a dot product is happens with the help of cos theta. So flux phi is equal to E dot vector A. That is the new equation arise, named as electric flux. Now that is point is obtained from the last point number 7. That is the key point to understand over here. Key point to understand over here. Now further one can understand electric flux. After electric flux, the new topic is there named as electric. Electric flux. Another new point is that, not a new point, it is same point, cos theta. Whenever there is a new equation, whenever there is a new equation, and if there is a theta angle, so we have 3 points to be note. Theta is equal to 90 degree, theta is equal to 0 degree, and theta is equal to 180 degree. So what? Theta is equal to 0. Everybody know cos 0 is equal to 1. Theta is equal to 90 degree. Cos 90 is equal to 0. And theta is equal to 180 degree. That is the minus 1. What do we understand? Now, you see, it is of 1. Means this point is 1 and theta is equal to 0. Theta is equal to 0 means what? E and A both are in same direction. The angle between E and A is same. Theta, we can understand the theta is angle between vector A and vector E. In the very first case, if both are same, means both are in same direction, they are parallel, equidistant each other, in same distance. If they are in same distance, the flux convert into a maximum value. So maximum value of flux is equal to E into A. If both are perpendicular, if both are perpendicular, see properly. If both are perpendicular, means what? Flux phi goes to 0, cos 90. And if they are opposite, electric field in this direction and direction of area vector is in this opposite direction, then one can understand there's a minus E into A, minus E into A. It is the minimum value. So that is the flux value. With the help of this, one can understand which charge reside at that point. That is what to be noted. So that is a flux. Main point of flux is this. It reside over here. That is the main point of flux is here. Flux identify the source charge. Which source charge is reside over there? That it identify. Try to understand. There is a clear cut point. Clear cut. And it is beautiful point. Flux identify the source charge. Flux identify the source charge. Or a plus minus. So if theta is 0, then that is a positive. Sorry. If theta is equal to 0, then that is a positive. If theta is equal to 180 degree, then there is a negative charge. By this way, one can understand where there is a positive charge, where there is a negative charge. By this way, one can understand properly. For positive charge, it is greater than 0. For a negative charge, it is less than 0. Clearly understand?
Yes.
Properly is too much interesting point. So if theta is equal to 0, flux is greater than theta is equal to less than theta is equal to 0, flux is positive. If theta is equal to 0, means flux is positive value. Positive value means flux is greater than 0. For theta greater than 0, or you can understand from 0 to 90, in between 0 to 90, it is a positive. From 0 to 90, it is a positive charge. You can understand up like this way. And if theta is equal to 90 to 180, is 90 to 180, between theta in between 90 degree to 180 degree, means how one can write down this way? Theta is equal to 90. That is a theta less than, and that is a greater than 90, less than 180.
Yes.
Nah, 190 થી વધારે, sorry, less than 90 and greater than 180. Like this is theta greater than 180. If you see theta greater than 90 degree and theta less than 180 degree, separate out. So you can understand. In between this way, you can understand flux 5 less than 0 means is negative. It have a negative value, means that is a negative charge. That is a negative charge. And here is positive charge. That is positive charge over here. There's a positive charge, negative charge. With the help of this, means that is the key point. One can understand that with the help of flux, one can identify the source. Identify the source, whether it's positive, whether it's negative. See how. See, one can understand. I draw a little structure by which or by mean you can understand properly. There's a flux phi is equal to E into A into cos theta. Understand? So that is say positive charge, and positive charge have outward field lines. Positive charge have outward field lines. Understand? and there is, you see, surface around it. Surface around it means there is a positive charge. If theta, what to understand value of theta, you can understand the positive theta value. Theta is an angle between area vector, that is the E for this, and if you set area vector this, so it is area vector A. If E and A are both in same direction, then you can understand theta is equal to 0 degree, and if theta is equal to 0 degree, then cos 0 degree is equal to 1, and if cos 0 degree is equal to 1, then flux phi is having the positive value, means there is a positive charge inside the source. Positive charge inside source. Positive charge inside the source. Source charge is positive. By this way, one can understand clearly, one can understand properly, clearly. Clear about this point?
Yes.
Second equation, same. Once I draw the negative charge over here, there is a negative charge. Negative charge is inward direction. Direction of negative charge is inward, like this way. And you see, just you draw the surface around it. Radial surface, it is radial. For the negative charge, you see electric field is inward direction, and if you draw the surface, the area vector is outward. So both are opposite direction. Here electric field and area vector is same direction. Here electric field and area vector both are opposite direction. So theta is about 180 degree. And if it is theta is 180 degree, then there is a negative. The flux phi is EA. So point to be worth note over here, there is a negative charge inside the source. Negative charge inside the source. Negative charge inside the source. There is a source charge inside the surface or inside the surface. Inside the surface, you can understand, inside the surface. Clear? And what happened if theta is 90 degree? What happened if theta is 90 degree? Mathematically we prove over here. Here mathematically prove, but by diagrammatically what happened? If theta is 90 degree, means electric field lines and area vector both are at 90 degree. What to understand? Suppose there is an area vector perpendicular. Understand clearly, beautiful concept. And if electric field lines is same direction, means electric, this is electric field, red line is electric field. You understand? Huh? There is an area vector and electric field both are in same direction. See, first case. It directly means this is the surface. You see properly. Electric field line is perpendicular to the surface. This is the first case, you see. First case, you see over here. Electric field and area vector both are in same direction, means if we remove this area vector and see that electric field is perpendicular to the surface, you see perpendicular to the surface. Clear cut idea over here. And in second case, if electric field is inward direction, so 180 degree, second case, if you remove, still it is perpendicular to the surface, still electric field is perpendicular to the surface. But what happened? What happened when theta is 90 degree? Means electric field and area vector both are at 90 degree. And you see the graph. Electric field and area vector both are at 90 degree. Means you remove the area vector, means electric field lines parallel to the surface. You see properly, electric field lines is parallel to the surface. That is the proper concept. Means what? That flux does not pass through the surface, but it is parallel to the surface. Flux does not pass from the, does not passing from that surface at any angle. It is passing touch to the surface only. Okay, understand this, keep this noting. So if theta is equal to 90 degree, means electric field is not passing from surface, but it is parallel to the surface. Electric field is parallel to the surface. You see once again, there is a surface and there is electric field. There is a perpendicular electric field and there is a parallel. Like this way, it is passing parallel to the surface. That's why no more electric field passing from the surface. That is the key point. So that is the real nature of flux. And with the help of this flux, one can identify the amount of electric field density. And that is the another concept given by Faraday, which is after some instant, after some time, you learn that topic. Means in this chapter, but after some theory, you can understand. But at least at this theory, electric flux is this. At least at this point, electric flux is this. Okay.
Okay.
So the definition of electric flux is that definition of electric flux that at any area is areal integration of vector electric field on that area. On that area, it is areal. That is the area. Areal integration means you see this surface is divided into dA parts, small amount of infinitesimal small part, and you just add all that infinitesimal small area and add it over here. So integration of areal with electric field gives you the flux. Gives you the flux. That is okay. It is at this point. We'll remain over here, stop over here, and we'll continue tomorrow from here.
Okay.
Okay.
Yes.